So today we're going to be looking at invertible matrices, and in particular, the building blocks of invertible matrices. So these are called elementary matrices. And the question we are going to be tackling today is this. So how can we classify invertible matrices? Now, one of the big facts that we talked about last time was that not every matrix is invertible. And this makes sense if we remember things like numbers. Not every number is invertible. 5, for example, isn't invertible if we consider only the system of whole numbers. In fact, no whole number other than 1 is invertible under that set. So some matrices are going to have inverses, that is, they're invertible, and some will not be. So this question of how can we classify invertible matrices is a really common kind of question in mathematics. And in algebra, this classification often comes down to the following idea. And that is, what are the building blocks of invertible matrices? Can we say what all invertible matrices are built from? And on the other hand, what all non-invertible matrices are not built from those building blocks, okay? So the building blocks only build up invertible matrices. Okay. So in fact, that turns out to be exactly what elementary matrices are. So to think about this in a more familiar context, we can think of numbers. So again, we're going to be trying to find these building blocks, but we have already been able to find building blocks of whole numbers throughout our lives, probably as far back as late elementary school for you. So, for example, if you consider something like whole numbers, again, they have building blocks, which we call the primes. So if we take the number 10, it has building blocks 5 and 2, because we can multiply 5 and 2 together to get 10. And 5 and 2 can't be broken down anymore under multiplication. The number 16 can be broken down into 8 and 2, but then 8 can be broken down into 4 and 2, and 4 can be broken down into 2 and 2. And so then 16 has the number 2 4 times as its building blocks. That is, it has 4 2s as building blocks. So we're going to try to do the same thing for invertible matrices. Find other matrices analogous to prime numbers that act as the building blocks for invertible matrices. And so our building blocks, as you might guess from the heading of this class, is an elementary matrix. So an elementary matrix is basically one that can't be broken down any further, and any further under multiplication. So a matrix is going to be called elementary if it is one row operation away from being the identity matrix. And if we just have the identity matrix as our building block, that's not going to be enough to build all of the invertible matrices. So we need more than just identity matrices. Elementary matrices are going to be just enough. So to get an idea of what an elementary matrix might look like, let's start with an identity matrix and do a row operation. And if we do a single row operation, we should end up with an elementary matrix, because we can do and undo row operations. So if we take the identity matrix with 3 dimensions, and we say take row 1 to row 1 plus 2 row 2, then we're going to end up with a matrix that just has one entry different than the first one. So it's 1, 2, 0, 0, 1, 0, 0, 0, 1. Okay, and then that's our elementary matrix. And so next you are going to go on and practice some of this, get a little bit more familiar with elementary matrices in your chapter activity packet. So the key to what you just did on your cap is that the multiplication by an elementary matrix corresponds to some row operation. And in particular, it's going to correspond to the row operation that is used to get from it to the from it to the identity. Okay, or from the identity to it, I should say. So we get this proposition that corresponds to this. And I think the key thing to this idea is you just always have to be careful, like which direction you're going to. You saw me, or you heard me pause there, kind of which direction does this go? I always just check it because my brain is never quite good enough to remember which direction is which, but my brain is good enough to always be able to check. So the proposition here is that if we do an operation, which we'll call star, to the identity, and we get an elementary matrix from that, and that will always be an elementary matrix because it's one row operation away from the identity, then EA, the elementary matrix multiplied by some other matrix, is the result of performing that row operation on A. Okay, so we now have multiplication of matrices as a way of writing row operations, or maybe I'll say that the other way around. Row operations can be written as multiplication. And so instead, like, I think row operations are kind of fuzzy to describe. Here we have row operations being described a lot more concretely as multiplication. So I'd like you to pause here, and before you go on to the next cap, also think about how we can solve this big question, the big question of being able to write invertible matrices in terms of elementary matrices, and how this result helps us. Okay, and then go on to the cap. Okay, so in cap 6.8, the first thing that you did was you found elementary matrices that could be multiplied by an invertible matrix, to transform it to A, or to row reduce it to, multiply by A to row reduce it to I3. And we know that since A is invertible, it can be row reduced down to I3. And so each of those elementary matrices came from our particular row reduction step. And we know that any invertible matrix can always be row reduced to the identity. So to be a little bit more specific and go into this even a little bit more, EK, because it's the first thing multiplied by A, comes from the first row reduction step. Okay, and then the second thing that we did was we then reversed our work from back to forth. So instead of reducing A to I3, we can then also do row reduction steps to go from I3 to A by just doing each one the opposite way. And in that way, we kind of write I3 equivalent to A. Okay, and remember again, same steps, just going from I3 to A in this case. So each of these steps is also going to have an elementary matrix, but this time we're going to multiply it by I3. So we could call these elementary matrices EI hat, that little mark on top of the EIs is pronounced as a hat in math. So we get this product, E1 to EK. We know it's going to be the same number of steps. We could also call it EL if we're not quite sure. In the end, it's not going to make a difference. And that is equal to A. And again, these came from the row reduction steps that were just reversed in the previous step. Now, it's important to note that each of these EIs is actually going to be reversible, or I should say invertible. Then that's exactly because we can reverse the steps. So let's take a look at that. What is going to be the difference between the elementary matrices that come from opposite steps? Okay, so if we have opposite steps, as in part 2, how do the elementary matrices in part 3 correspond to the elementary matrices in part 2, or in part 1, I should say? So for example, if we have, it's usually easier for me to start with the identity. Okay, so if we have a matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, and I want to take R2 and go to R2 minus 3R3, for example, then the only row that's going to change is the second row. So I know that the first row and the third row are going to stay the same. And then the second row is going to be 0, 1, negative 3. Okay. Now, if I then want to get back to the identity, to like reverse this, then what do I have to do? Well, the only entry that needs to change is that negative 3. And so I have to take R2 to R2 plus, well, I wrote 1/3 there, but I can actually see now that that's a mistake, and I think I'm going to realize it very shortly in my writing, as soon as I actually try to write the 1/3. This isn't like a multiplicative inverse. It's going to be an additive inverse. Yeah, and you see there I realized, oops, I need the additive inverse. Okay, so I'm going to need the plus 3, R3. Yeah, there we go. And then we get the 0, 0, 1. Okay. And so here we have two opposite row reduction steps. Now these are the matrices that I get from the identity when I carry out these row reduction steps. In the theorem, they're the matrices that I need to like reduce something to I under the row reduction step. So I have to be like a little bit careful about exactly what matrices I have, but they're going to be very close to these if you double check what they are. So the one that I highlighted is certainly one, and it's the one, yeah, it's the matrix that reduces to the identity under the first step that I highlighted, and then that second one that I highlighted, I don't think I've written down the corresponding elementary matrix, but you can imagine that it's just going to be the one that has the positive 3. Okay, now we're going to prove our main classification theorem. And I've just written the reasons why, if we're given an invertible matrix, we can write it as a matrix that can be row reduced to the identity, just like we've assumed before. So that means that from our previous exercises, we can find elementary matrices corresponding to each step in the row reduction process, such that their product times the identity is going to equal our matrix. Because if it can be reduced to the identity, then the identity can also be row reduced, or perhaps we call it row increased, to the matrix A. Okay, so in other words, our matrix A itself is equal to the product of these elementary matrices because the identity multiplied by anything is just itself. So in part 2, the second direction, we need to instead assume that we are given the product of elementary matrices, and we want to then show that it is an invertible matrix. So instead, we want to show that the product of elementary matrices is in fact invertible. So there are a couple different steps to this, and both of them are almost so simple that it's difficult to see exactly what to do. One lemma is to show that if we just have one thing in our product, if we just have one elementary matrix, then EI itself must be invertible. And essentially we can think of this as coming from the idea of doing a row operation backwards, like we did before.